Now I'm going to share my screen and we're going to first take a look at the course, see the things that I've added, and then we'll get to our lesson for today on section 6.1. All right. So here we are. Here's our course in the student view. It's what you guys see. So here's our calendar. As you can see, I've already started adding things for today. If you'd like to see the presentation I'm going to use today, you're more than welcome to open that and follow along at your own pace if you like. The recordings will go here. And if you notice, we have chapter 6 available. The entire unit of notes and resources is posted. I am working on the assessments between classes today. Hopefully I'll have those ready later today. If not, they'll be ready tomorrow. So we have lots of things here. Also, if you have not done the survey from last week, please do so. All right, it's right here. You can get to it. Really short, 2 questions. Help me communicate with you better. I appreciate it. If you have, awesome. If you don't remember if you did, it only allows 1 submission per email address. So if you try to do it and it says you already did it, you already did it. All right, moving on. So chapter 6, here's what this is going to look like. So section 6.1, we're going to go through that lesson today. It's going to feel a little fast, but don't stress. We're going to go through the notes today. It's going to be mostly just a lecture and notes today. See some examples. And tomorrow we'll do work. All right, we're going to do some work on our own. We'll do some breakout rooms. We'll do some examples as a group, right? And we'll really get a better idea of how these things that we're going to go over today work. If we go into the notes and resources for section 6.1, it's going to look really small here. So I'm going to open up the modules here so we can see these things easier. So here's our 6.1 notes and resources. As you can see, I've got things kind of broken down here. At the top, we have notes. These are the notes / study guide that I've created for section 6.1. Right, this is not the same as like the PowerPoint or anything like this. It is a document. And yeah, it's good stuff. This covers everything we're going to do in section 6.1. It has definitions, examples, formulas, right? Hopefully it helps, gives you another way of looking at and digesting the content, right? So we got a lot of good stuff in here. There's one of these for each section. All right, so section 6.1, 6.2, 6.3, and I'll continue with the rest of the chapters as well. If you want to download and print these notes, you're more than welcome to, and do whatever you want to do with notes. Then if you like, I also have the presentation for today right here. This is so there's some like ready to go PowerPoints from the textbook. So I'm using one of those today. It seemed to work pretty good. Covered all the stuff I wanted to cover. And it helps me devote my time to more important things and developing other resources for you guys. Here's our AP Daily videos. We also have worked examples from the textbook. These are also videos. All right. And I also have some calculator instructions. This shows you how to input random variables into your calculator. So you can have the calculator find your mean and standard deviation and things of that nature. You can watch a short video about it, or you can just look at the pictures showing you how to do it. Either way, this might be something good to refer to. It could be helpful. All right, so that's kind of what the notes and resources will look like. If there's things that I think will help, I'll add to the notes and resources for that section. The idea is that everything for 6.1 is in one spot. All right, and then everything for 6.2, all the stuff for chapter 6 all together. So each of these looks like that. We also have our practice problems and solutions, right? There's problems, those are solutions. Please try to do the problems before you look at the solutions, all right? At the very least, look at the problems and try to think if you know how to solve it before you look at the solutions. The solutions are provided so that you can see if what you're doing is correct or not. It's a learning tool, right? And this again is just a document full of problems. All right, these have been selected from the textbook exercises because I thought they were good problems that help practice the skills that I think you need to practice. All right. And then lastly, there's going to be the assessments, which again, I'm working on, should be done. At least the multiple choice, I think, will be done later today. And I may or may not be able to get the free response question / self-assessment completed today. We'll try, but yeah. All right. So again, that's what this new resource looks like. And then again, if you're looking for class recordings, or specifically what we did on any given day, you're going to look at the calendar. The modules will just house everything for a specific chapter and sections. Right. And again, as everything else I've done for the course and things that I work on and create for you guys, please let me know what works, what's not working, what you would prefer to have more of, less of, so on and so forth, so that I can continue to improve the course to benefit you guys the best. All right, so please keep that in mind. So here we go. Chapter 6, random variables. Section 6.1 is on discrete and continuous random variables. And again, this was created by the people who made our textbook. All right, so here we go. In this section for this lesson, right, you should be able to, after we're done, compute probabilities using the probability distribution of a discrete random variable, calculate and interpret the mean expected value. Those terms are interchangeable now. Mean and expected value refer to the same thing, of a discrete random variable. Calculate and interpret the standard deviation of a discrete random variable, and compute probabilities using the probability distribution of certain continuous random variables. All right, so again, we're using a lot of what we learned in the previous chapter about probability in this new chapter 6. We're working with mean and standard deviation, which means we will also be dealing with variance. All right, and then probabilities, right? We're going to be using things that we did in the last chapter about probability. We're going to be using table A. We're going to be using z-scores. All right, normal distributions are going to pop back up again. These things aren't going away. All right, does anyone need a moment to write anything down from this screen? Raise your hand. Excellent. All right, now is an excellent reminder in time to let you know you should be taking notes. Many of you guys in your reflections last semester said that you wish you had more notes. To have more notes, you have to write notes. If you do not have a notebook, please go to the high school, go to Orange Glen and get one. We ordered a bunch of graph paper comp books. So if you don't have a notebook, they're for free. Just go and ask for one. All right, we got them specifically for the math department. All right, that was the one thing that we asked for as a department. We're like, we want notebooks for our kids. So if you need one, go get one. It's free. All right. So random variables and probability distributions. A probability model describes the possible outcomes of a chance process and the likelihood that those outcomes will occur. Consider tossing a fair coin 3 times. We're going to define the variable x, it's a capital letter X, to be the number of heads obtained. All right, so x just tells me, it keeps track of how many times a head pops up when I flip a coin 3 times. Right. Given this context and what x represents, there are 4 possible values of x. We can have no heads, in which case we have all tails, right? We can have 1 head pop up, in which we could do a head first, have a head come up second, or have a head come up third, and the other 2 flips are tails, right? We can have 2. We can have 2 heads pop up first, 2 heads separated by a tails, or 2 heads last. And lastly, we could have 3 heads, in which case every flip is a head. Those are the only options. There's no more, no less. All right, I can't have a negative number of heads. I can't have any more than 3 because I'm only flipping the coin 3 times. So the variable x represents the different possible number of outcomes that are successes, so to say, right? Having a head is a success. We can think of it that way. The probability model could be a table, as in here, where we have the values that x can be along the top, 0, 1, 2, or 3, and the probability or chances or likelihood that each of those values occurs based on the total number of outcomes. Right? There's 1 out of 8 ways to get no heads. 3 out of 8 for 1, 3 out of 8 for 2, 1 out of 8 for 3. We can also choose to represent this with a histogram. Right? That's another probability model to demonstrate, to show the distribution. Right? We can have 0, which would be 1/8, 1 3/8, 2 3/8, or 3 1/8 again. Right? We get this symmetric distribution. Right? A random variable takes numerical values that describe the outcomes of some chance process. The probability distribution of a random variable gives its possible values and their probabilities. All right. So x, right, is our random variable, and this table or the histogram are the probability distribution. Right. This would be the probability model. Right. I can show the different outcomes. So discrete random variables. Right, there are 2 main types of random variables. We can have discrete or continuous. If we can find a way to list all possible outcomes for a random variable and assign probabilities to each one, we have a discrete random variable. So that's the definition we're going to get first here. A discrete random variable x takes a fixed set of possible values with gaps between. Probability distribution of a discrete random variable x lists the values x sub I and their probabilities p sub I in a table like this. Value x sub 1, x sub 2, x sub 3, probability p sub 1, p sub 2, p sub 3. Now these subscripts, when we use I here, it's saying that this is the ith, whatever number value in my number of outcomes. So when we look at the coin example, flipping a coin, we had the first x value was 0. So x sub 1 would be 0. X sub 2 is 1. X sub 3 is 2. X sub 4 is 3. That means the first possible number of outcomes was 0. The second was 1. The third was 2. So the subscripts just tell me which value, not the actual number value, but which value along my set of values this thing was. Was it the first, the second, the third? And then the same subscript with the probability p sub 1 means this is the probability that the first outcome occurs. This is the probability of the second outcome. This is the probability of the third outcome. And we use these subscripts to show that these values are not the same. Right? X sub 1 may not be the same as x sub 2. So we have to use a notation that shows that it could be a different value. Same with the probabilities. P sub 1 might not be the same as P sub 2. Because these are possibly different values, we have to show that with a notation, and that's the subscript. The probabilities P sub I must satisfy two requirements. Every probability P sub I is a number between 0 and 1. This is the same as what we saw in the previous chapter, where probabilities have to be between 0 and 1. The sum of the probabilities is 1. Again, that's a valid probability model, right? When you add up all the probabilities, they add up to 1. Can't be more than 100%. To find the probability of any event, add the probabilities P sub I of the particular values X sub I that make up the event. Okay, so for example, if I wanted to know the probability of flipping a coin and getting 2 heads, right, that's a specific event. Right. On our previous example, there was a 3/8 chance of that happening. 3 out of 8 possibilities. If I wanted to know what's the probability of getting at least 2 heads, that would be the probability of getting 2 heads plus the probability of getting 3 heads, because that's at least 2 or 3. So I would add those two probabilities together because those two things make up the event. All right. Is there anything I can clarify? So now the mean or expected value of a discrete random variable is what we'll talk about next. When analyzing discrete random variables, we follow the same strategy we used with quantitative data. We're going to describe the shape, center, and spread and identify outliers. The mean of any discrete random variable is an average of the possible outcomes with each outcome weighted by its probability. Right? Previously, when calculating a mean, we just added up all the possible outcomes and divided by the number of outcomes, or the number of things. But that was based on each outcome being equally likely. Now the outcomes are not equally likely, so we have to take that into consideration. So suppose that X is a discrete random variable whose probability distribution is a table of values and probabilities. To find the mean or expected value of X, you're going to multiply each possible value by its probability, then add all the products. All right. So we have to take an extra step, right? Value X sub 1 times P sub 1 plus X sub 2 times P sub 2 plus X sub 3 times P sub 3, right? We take each outcome, multiply it by its probability, add all those up. That's how we determine the mean for a discrete random variable. Right. With notation, it looks like this. Mu sub X, and again, mu is what we've used to notate the mean, is equal to the expected value of X. We can use this notation as well, capital E, parentheses X, or whatever your random variable is, X, Y, Z, whatever it's been given, equals X sub 1 times P sub 1 plus X2 P2 plus X3 P3, and so on until you run out of X's and P's, equals the sum, that's what this Greek letter sigma, capital sigma, represents, means sum, add everything up, of X sub I times P sub I. And again, the letter I is just a placeholder saying I'm going to use all the values of X times all the values of P, but they pair together, X1 with P1, X2 with P2, X3 with P3. All right. So that's what this will look like in notation, and we will look at an example here next. Right. So now, let's look at an example. A baby's APGAR score is the sum of the ratings on each of 5 scales, which gives a whole number value of 0 to 10. Let X equal the APGAR score of a randomly selected newborn. The APGAR score can take on values of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each of those outcomes has the given probabilities here in the table. We're going to compute the mean of the random variable X, and then interpret this value in context. Okay. If we look at this table, we can see that 1 in every 1,000 babies would have an APGAR score of 0, 6 in every 1,000 babies would have an APGAR score of 1, and so on. And that's just converting the decimals into kind of like solid values. So the mean expected value of x is, we've got our notation up here, it's going to be 0 times 0.001, that value times its probability, 1 times 0.006, again, the value times its probability, plus 2 times 0.007, plus 3 times 0.008, 4, 5, 6, we'll go on until we get to 10 times 0.053, which will ultimately give us the outcome of 8.128. Right, so over many trials of randomly selecting newborns and looking at their APGAR scores, we would have an average or expected APGAR score of 8.128. Right, so the mean APGAR score of randomly selected newborn is 8.128. This is the average APGAR score of many randomly chosen babies. Right, and we use that term expected value because based on the probabilities that we know, right, based on statistics, we can say, hey, over many trials, this is what we expect an APGAR score to be. That way we don't have to run more simulations, we can use the given data. Next, standard deviation. Right, since we use the mean as a measure of center for a discrete random variable, we use the standard deviation as our measure of spread. The definition of the variance of a random variable is similar to the definition of the variance for a set of quantitative data. Recall that we determine the variance with quantitative data as the difference between the mean and our outcome squared. Right, that gives us, and then we add up all those different numbers and we get our variance. Right, similar kind of thing happens here. Suppose that x is a discrete random variable whose probability distribution is given between values and probabilities, and that mu sub x is the mean of x. The variance of x is given with the following crazy formula. Right, we can use this var parentheses x, or we can use the notation sigma squared sub x. And this is lowercase sigma, equals the difference between first outcome minus the average squared times the probability of the first outcome. So again, we have this multiplying by the probability of a given outcome that occurs in the variance, just like it did in the mean. Right, then second outcome minus the mean squared times the probability of a second outcome, and so on, and we continue like that until we don't have any more outcomes and probabilities, and we can write that in short notation as the sum of all the differences between outcomes and mean squared times those outcomes probabilities. Right, we need the variance, because to get the standard deviation of a random variable, you need to take the square root of the variance. So once you calculate the variance, you just throw that under a square root and hit enter, and you have your standard deviation. Or you can put all of this under a square root and hit enter and get it in one shot. That's up to you. Right. So again, standard deviation is the square root of the variance. See an example. So back to our APGAR scores, same value table and probabilities from the previous example. We're going to compute and interpret the standard deviation of the random variable x, which is APGAR score of a randomly selected newborn. Right, the formula for the variance is given. Sigma squared sub x equals the sum of x sub I minus mu sub x, or the outcome minus the mean, squared times the probability of that outcome, p sub I. So we calculate variance, right? Sigma squared sub x, which is 0, value here, minus our mean, squared times the probability of getting 0, plus 1 minus the mean, squared times the probability of getting 1, plus 2 minus the mean squared times the probability of getting 2, and so on until we get to the last possible outcome of 10 minus the mean squared times the probability of getting 10. Putting all that in your calculator, you'll get the variance of 2.066. But wait, we're not done. Right, standard deviation of x is sigma sub x, which is equal to the square root of the variance. Right, we got our little square root of the variance, 2.066, and we get 1.437. Right? So we've now computed our standard deviation. What does that mean? It means that typically the APGAR score of a randomly selected newborn will vary by about 1.437 from the mean of what was the mean? 8.128. All right. So that's what we will say. A randomly selected baby's APGAR score will typically differ from the mean, 8.128, by about 1.4 units. All right. When you have to round your answer, which typically when you're taking the square root of some random number, you're going to get a crazy decimal. You're going to round it. Don't say, it's wrong to say that it will typically differ from the mean by 1.4 units, because it's not exactly 1.4. It's about 1.4, or roughly, or approximately, or close to, right? You want to use some verbiage that says that it is close to, but not exactly that number, because you're rounding. So now we're going to move to continuous random variables. Right? Discrete random variables commonly arise from situations that involve counting something, counting the number of heads, right? The possible APGAR scores, right? It's something that is countable. 1, 2, 3, 4, 5, you know. Situations that involve measuring something often result in a continuous random variable. Right? This is because it can take on any value between a certain range of numbers. Right? I can't account for each of them. And there's mathematical reasons for this, but yeah, we won't get into that. Right? A continuous random variable x takes on all values of an interval of numbers. Right? The probability distribution of x is described by a density curve. The probability of any event is the area under the density curve and above the values of x that make up the event. So essentially, it's kind of like what we did with normal distributions, right? We can have any value along our horizontal axis be an outcome that's within our interval, our range for our statistic. And we use the area under the curve to determine the probability, right? The probability model of a discrete random variable x assigns a probability between 0 and 1 to each possible value of x, right? And that's with discrete, right? Each individual outcome can have a probability, and we put that in a table, or we can show it on the histogram. A continuous random variable y has infinitely many possible values. That's where we come to a problem, right? Between 0 and 1, there's an infinite amount of values. No matter what value you give me, I can give you a value bigger or smaller than that between 0 and 1, right? So there's a problem. Right? All continuous probability models assign probability 0 to every individual outcome. Only intervals of values have positive probability. All right? So if you're asked to find the probability of y equaling 1.3, right, on a continuous random variable, it's going to have probability 0. Right? And this is because a horizontal line, essentially, which is what would represent that single value on a density curve, has no width, which means it has no area. So it's equal to 0. All right. So we'll look at an example, and it's basically what we did in the previous chapter with our normal distributions, because we've already been doing stuff like this. We just didn't call it a continuous random variable yet. Okay. So here's our example. Right? The heights of young women closely follow the normal distribution with mean of mu equals 64 inches and standard deviation of sigma equals 2.7 inches. Now choose one young woman at random, call her height y. So y is a continuous random variable representing the height of a randomly chosen young woman. If we repeat the random choice very many times, the distribution of values of y is the same normal distribution that describes the heights of all young women. Right, so that's the normal distribution that we already have defined up here. Our problem that we want to solve is what's the probability that the chosen woman is between 68 and 70 inches tall? So now we have an interval of values between 68 and 70. Right, so step one, we're going to state the distribution and the values of interest. Right, the height y of a randomly chosen young woman has the distribution normal with a mean 64, standard deviation 2.7. We want to find the probability that y is greater than or equal to 68 and less than or equal to 70. And this just throws us right back into what we did with normal distributions previously. We're going to need to find the z-score of 68 and 70 based on the normal distribution. There we go. So perform calculations and show your work. So here we go. Standardized scores for the two boundary values, 68 and 70, are here. So remember, z equals your outcome minus the mean divided by the standard deviation. That's how we get a z-score. You're going to want to remember this. This formula is not going to be provided on your formula sheet for the AP exam. So this is one you're going to want to remember. All right, so the z-score for 68 is 1.48. The z-score for 70 is 2.22. Okay, so let's go back to what we have done. Right, so if we look at the normal curve, somewhat like, oh, that's so bad. Try that again. It was ugly. All right, try again. That's better. All right, so we'll have mean and 3 standard deviations to the right, 3 to the left, right? So 1.48, right? Both of these are to the right. We're saying 1.48, we'll say is maybe like right here. 2.22, I don't know, about right here. So this is the only area we want. And remember, table A, which is what we'll use to now solve this, will only provide the area under the curve to the left of a given z value. All right. So the next step, right, if we want to find the probability of z being greater than or equal to 1.48, right, to the right of 1.48, less than or equal to 2.22, to the left of 2.22, so that's our shaded area, then we have to take the probability of z being less than or equal to 2.22 and subtract the probability of z being less than or equal to 1.48, right? And this is because, right, our table A gives us the area to the left of 2.22 and the area to the left of 1.48. I don't need the area to the left of 1.48. I just want what's between here. So to isolate this chunk, I take this whole thing and subtract the extra arrow, which is this here. So then we get 0.9868 from table A minus 0.9306 again from table A, and we get 0.0562. Okay. Is there any questions about how this was done? All right, and then again, what this means is that if we randomly choose a young woman, we have about a 5.6% chance of selecting someone who is between 68 and 70 inches tall. That's what our result means in context. Right. So anyone need a moment to write anything down? Please raise your hand. All right. And there we go. We have covered what we need from section 6.1, discrete and continuous random variables. We have computed probabilities using probability distribution of a discrete random variable. We can calculate and interpret the mean of a discrete random variable, calculate and interpret the standard deviation of a discrete random variable, and compute probabilities using the probability distribution of certain continuous random variables. All right. Now, I know this went fast. And that's, again, it's kind of the boat we're in, so I do apologize. However, here's the good news. Tomorrow is all practice. We're going to get problems, we're going to work on stuff, we're going to learn how to do this in practice. All right. So tomorrow, please make sure you have a calculator ready. You're probably going to want table A available. And you may need like your phone. You might have to take pictures of things that you might be working on in scratch paper to share with people you're working with. So you might want to have those things ready. Stop sharing my screen here. So yeah, tomorrow is all going to be about using these things and practicing these things. We'll do some stuff as a whole group. We'll do some breakout room where you'll work with small like groups of like 3 to solve some problems and then come back and share what you've done. So hopefully we'll get to see lots of examples tomorrow.